Welcome
Everyone.
back. I see you're back, Dan. What's up?
I am. And Neil is also with us. Hi, Neil.
Hi, Neil.
Hello, how are you? Good day. I can't really say good morning or good evening because I think everyone's scattered all over, but it's closer to evening where you are, but good day.
Exactly. So no one knows now. I was just looking at the attendee list, and yeah, there are people from all over the world. I mean, we used to do this with the attendees from Romania and neighboring countries when we were doing in person, or from Europe at least. But now we have people from Argentina, from Japan. It's really cool.
So I hope everyone just had a time of day appropriate refreshing beverage.
Coffee it is.
Certainly for me.
Well, Neil, before we start, if I may, I have a little question for you. So
Sure.
I saw in your bio that you're director, you're software architect and Meme Wrangler at ThoughtWorks. And I was wondering, what's a Meme Wrangler?
ThoughtWorks is one of those companies where you get to make up your own titles, but you only get one set of business cards, so you can't have more than one title at a time. And when I started ThoughtWorks about 15 years ago, my first set of business cards actually said software application architect on them, just application architect. But then I realized at that time, and it's actually gotten better recently, but at that time in large organizations, software architect mostly meant post-useful. That meant didn't write code anymore, just did like diagrams, and that's not what I wanted to be. So when it came time for my next round of business cards to come up, I came up with a much more inventive Meme Wrangler. Meme, of course, is a viral unit of thought, which was first defined by Richard Dawkins in The Selfish Gene. And then Wrangler actually has two useful English meanings. One is to sort of herd and organize, and the other is to handle and mediate disputes for arguments. And I figured I'd do both of those things on a regular basis. And so I'm sort of a herder of ideas. But it's interesting that, you know, sometimes titles become self-fulfilling prophecies, because many of the books that I've written are actually exactly from that. Is I'm actively looking for what's something that's interesting or unusual in the software world that I can wrangle as a meme. And so it's become sort of a self-fulfilling prophecy.
But this is the best title ever, you know, especially when when you explain like I was, if I were a Meme Wrangler, I would just send funny pictures to the whole Slack. So I think you've made a much more productive use of this title.
Well, it's funny because it's such the early days of the internet that the concept of an internet meme didn't exist when I created the title. So meme was not something that was very common. So it's actually the internet's come and overtaken me.
Well, it's absolutely brilliant. And I know you also, well, you've written many books, but one of them is about the fundamentals of software architecture.
Yes, the most recent one.
The most recent one. And is this in any way related to your talk on architecture foundations?
It is. In fact, this material is derived directly from that book.
Well, that's great. Fact, then we should buy it.
You should. In fact, my advice is always you should buy 2 copies in case you lose one.
It's what I do.
And, you know, technical books are fantastic gifts for your mother or your spouse or your cousin or, you know, I mean, you know, O'Reilly really just says loving, you know, from your spouse. So I think that's it.
Thank you. This is a great, it's a great Christmas present.
Well, that solves my dilemma for this year.
Exactly. See, I've solved multiple problems today, not just architecture, but I can get you your holiday gifts. So can you see my screen okay?
Loud and clear.
All good.
All right. So great. Let's talk about software architecture foundations, styles and patterns. As I was just chatting with Vlad, this is derived from mine and Mark Richards' most recent book. And what we wanted to do was, what if software architecture were brand new right now? What if it were a brand new thing we just invented last week? How would you rethink some of the kind of core assumptions and other things that have been living in software architecture? And so we created this content. So here's my agenda for today. This is all pulled from our book, but I can give you I'll give you a link to a website at the end that has more info. And in fact, all the diagrams that I'll show you today are on that website in one form or another, if you want to play with them. So I'm broadly going to talk today mostly about architecture styles. Architecture styles are these well-known patterns, mostly structural patterns of how components fit together. And each of those has a well-known set of characteristics and properties. And they all have names, and it allows us to have a catalog of known things as architects that we can talk about. I'll also briefly touch on the idea of patterns, and patterns are things that are independent of a particular style. So for example, CQRS, Command Quality Responsibility Segregation, you could implement that pattern on top of any one of these architectural styles. So a style is really just a description of the structure of the architecture. And you'll notice one of the separations I have here is between technical and domain partitioning. So let me describe what I mean by that. So think about an architecture that I'm sure you're familiar with, the traditional layered architecture, which has a presentation layer, a business rules layer, persistence layer, and a relational database. You're all very familiar with this architecture, I'm sure. In fact, some of you are probably working on a system that looks like this. And this is certainly one logical way to organize the components within this system around technical capabilities. But it's not the only way to organize those components. And what you find often when you build an architecture like this is domain concepts get sort of lost in here, because where does catalog checkout live in layered architecture? Well, parts in the presentation layer, parts in business rules, parts in persistence, parts in the relational database. And so you've taken that domain concept and sort of smeared it out across your architecture. An architectural style that's become quite popular in the last few years is this idea of a modular monolith, which is still deployed as a single thing. It's still a monolithic architecture, but the top level partitioning is around domains, not around technical capabilities. And organizations discover when you organize things around technical capabilities, what you do is you drive up the amount of communication overhead needed to work on common things. Because if I need to change catalog checkout in the layered architecture, it involves many, many teams of people. Whereas if everyone involved in catalog checkout is on the same team and working on the same component, then that change becomes much more trivial. And so this is an example of domain partitioning versus technical partitioning. And that's actually my top level organization of my architecture styles. I have these split between generic and domain specific. The generic ones are the ones we're most interested in because these are general ways to solve problems in architecture. But you can also build architectures that are highly tuned to just one kind of architecture characteristic. Those are the domain specific ones, and I'll talk about those briefly toward the end. So let's talk for a second about our friend, the layered architecture. It's really important, and one of the I can't go into great detail about any of these today because I don't have enough time. So what's really important here is to understand the underlying philosophy of this architecture. Why does this architecture exist, and what are we trying to achieve by building something in this architecture? And so when you look at the traditional layered architecture, with distinct technical layers, the real concern here is separation of concerns, having good separation between those layers. And in fact, a common feature of these architectures is this idea of having closed layers, meaning that all requests must come from the layer above, that you can't arbitrarily just leap into one of the layers in this architecture. And that, of course, is to give you isolation and separation of concerns so that if I need to change some code, it doesn't ripple out to a whole bunch of other places. And so separation of concerns is one of the big goals of this architecture. There are lots of hybrids and variants of layered monoliths. So a monolith is basically any code base that's deployed as a single unit. And sometimes a single deployable thing like a single jar file or area file, but it could be a web application where a relational database changes and the back end, the front end are all deployed in lockstep. So even if it's in multiple pieces, it can still be considered monolithic architecture. And so any of these variations are common in this architectural style. One of the things that you have to worry about as an architect is governance. Let's say that you design this layered architecture for very good reasons, but then the reporting team comes to you and says, hey, going through all those layers is taking too much time. We need direct access to the database for performance reasons. Should you allow them to do that? Probably not, because what you're going to end up with is a big ball of mud. Allowing them to break all the rules that you've set up is not a great way to build a long-lived architecture. But this sort of begs the question, well, what if you're in an organization where it's better to ask forgiveness or to beg forgiveness than ask permission? Well, this is the subject of my book one ago, Building Evolutionary Architectures, which is this idea of automating architectural governance. And there are tools available. ArcUnit is one of them that actually allows you as an architect to codify these structural rules as a unit test. Notice this test says no classes that reside in a package service should access classes that reside in a package controller. And so this allows you as an architect to automate the governance to make sure that they have chosen that correct architectural style. There are a wide variety of tools now available to architects to allow you to write very declarative rules about what your architecture should look like. ArcUnit is in the Java world, NetArctest is in the .NET world, so more and more of these tools are showing up in popular platforms. So the real drivers for this architecture, very much simplicity and cost. Very cheap to build, very easy to understand, and so if schedule pressure is one of my biggest drivers, this is not a bad architecture because it's easy to build and easy to understand. Let's look at the more interesting monolithic architectures. Microkernel is the next one, or also known as a plug-in architecture. And the core components here are a core system and then plugins that drive a differing behavior. So the core here is meant to have minimal functionality, general business rules and logic, but no custom processing and customizations driven through plugins. Now there's a spectrum here for microkernels because not everything that has plugins is necessarily a microkernel. If it's fully functional without the plugins, then it's probably more like just an architecture that features plugins. If the plugins are critical for it to actually function and only the core bits of the system work in that core, then it's much closer to a true microkernel. And in fact, the biggest example that many of you have probably used of a real true to form microkernel is Eclipse. Eclipse by itself does virtually nothing. All of its behavior is driven through those plugins. But there are lots of other tools that follow this architectural pattern. For example, an insurance company where you could build common insurance rules in the core and then have plugins that drive all the customizations for different states, for example. The real complexity in this architecture comes with the contracts between the core and the components. And in fact, the simpler version of this architecture has the only plugins only talking to the core and not talking to one another. That's when the real monstrous complexity comes into this architecture. And of course, Eclipse very much suffers from that because then you have to start, because the core has to be the thing that allows them to communicate, and you get into transitive dependency management and a bunch of other headaches. And so this architecture definitely works best if you can make the plugins essentially stateless outside of the core and let them only talk to the core. Another good example of this architecture is something like a source validation tool, where I can have the core scan source code for me and apply rules, but without any rules, all I'm doing is scanning the source code. So that's a good example of, to be a true microkernel, it needs to be essentially not, or just barely functional without any of the plugins in place. So the drivers for this architecture are a very specific kind of modularity. In fact, customizability is the real driver for this architecture because it allows you to customize things very easily through those plugins. But it also has well-defined deployability characteristics. You've all used a tool that says, copy this component to some directory and restart the tool. That's so it can load a new plugin. So a very well understood architecture. You'll notice the other icon that I have here is this quantum measure, and I don't have time to go into the full details of what that means, but you'll notice that there's a Greek columns and then sort of molecules, that indicates whether this thing is deployed as a single unit or deployed as a distributed architecture. The two I've just talked about, layered microkernel, are typically deployed as a monolith, as a single unit. Let's talk about a few event-driven or distributed architectures. And the first of these is just event-driven architecture. Now, a lot of architects use events in higher order architectures like microservices, but you can build entire architectures just on top of message queues and event handling. And that's what I want to talk about here, because it's one of the few architectures that give you both performance and scalability at the same time. It's actually a very hard thing to achieve, and this architecture can achieve that with a few trade-offs. Now, one of the interesting things about this, these two topologies, there's two flavors I'll talk about here, two structures, broker and mediator. Of the two, one of them gives you higher performance and scalability, and I'll ask you to identify which one when we get to the end. So both of them have event channels and the idea of messages and events. A broker has no central coordination, so it's just the event processors and event channels. And so when a message comes in, it reacts to it and then potentially passes it on to another one which reacts to it, etc. So for example, if I have some sort of business process in a broker style architecture, like a change of address for an insurance company, that you move message will go to customer process, which will process it and then post a message to anyone interested in a change of address. Turns out both quote and claim are interested in that, so they'll pick it up and process it, post a message to anyone who's interested in that change, and this workflow will propagate throughout my entire architecture. This is what's known as choreography, because there's no central coordinator here. All of these are just reacting to events that occur within this ecosystem. Error handling is much more difficult here because I don't have central coordination. But evolution is much easier here because now if I need to add a new, for example, process, that's trivial. If I want to send a unified notification to customer, that's also tricky because in asynchronous systems, having that kind of coordination, you have to be very careful and basically handle it yourself. The other kind of event-driven architecture is a mediator topology. And in this one, you have the same components we saw before, but with the important addition of a mediator. This mediator acts as an orchestrator, as a way to programmatically define what you want that workflow between those components to be. So Apache Camel is an example of one of these, Spring Webflow. There are an enterprise service bus typically has choreography built into it. So this is an architectural pattern that has many implementations out in the world. If you look at our business process here, it's much simpler because I can define that business process in my process engine using some sort of language or pseudo language. This is a great example of orchestration as a communication style. Error handling is much easier here in a mediator because I have that processing engine to handle errors and other things for me. In fact, I can build pseudo-transactional coordination here. A lot of the tools like enterprise service buses, that's one of the things they offer is pseudo-transactional coordination at the mediator level. But evolution is more complex here because I have to make a change to two places. I have to add not only my audit process, but also I have to add that to the mediator because that's what's driving all the workflow in this architecture. So nothing happens behind the scenes here. It all happens through that mediator. So the drivers for this kind of architecture, very much specific kind of modularity, high degree of agility and fault tolerance, really high scalability and performance, as I mentioned before. But of the two, which one gives you higher levels of scalability and performance? It turns out it's broker because there's less coupling one of the superpowers that we've learned in architecture is if you want high performance, the less coupling you create and the less messaging you create at the network level, the better off you are. And that's one of the things that this architecture broker in particular does really well. That mediator acts as a coupling point and becomes a bottleneck for a super high performance. You can still get great performance and scale out of both, but definitely better out of broker, which is one of the reasons you see it used so much in microservice architectures as a way to do performance tuning. Also very adaptable and evolvable. So there's an important distinction between those two things. Something is adaptable, you can add more behavior onto what's there. Evolvable means fundamentally changing how things work without keeping the old stuff around. So that's the event-driven architectures. The other one that's in this sort of family is the old school orchestration-driven enterprise service bus. This is probably the most complex technical partitioning we ever created for an architecture. And it was all about taxonomy and reuse. So this is designed to be an enterprise-wide thing. The real identifying characteristic of this style of architecture is this idea of a service taxonomy, or a very strict organization of how things are organized, organization of components and workflow in this architecture. At the top, we had business services. These are very coarse-grained things owned by business users. So there's no code here. It's all interfaces and schema, documents, etc. This was meant to define the fundamental things we do as a business at a very coarse-grained level. If there's no code there, then there has to be code somewhere, and that's where the enterprise services were. And these were also coarse-grained, but at a different level of granularity than the ones on the top, because the idea was, part of the goal of this architecture was, look, if we can build these enterprise services to be reusable in just exactly the right way, there will eventually come a day when we don't have to write any more code at this level, that all new application development will just be business users using some kind of BPEL tool, business process execution language, or some orchestrator to wire together new workflows, because we will have solved everything we know about customers and sales and all that sort of stuff. That was not true, because that ignores the reality that the world is constantly shifting and changing. But that's part of the goal of this service taxonomy was, let's build these reusable Lego blocks and then build this orchestration tool in the middle, this message bus, to wire all those things together. The one-off things that weren't meant to be reusable were called application services. So if only a single team needed something, they could go there. These were all things like logging, monitoring, etc. The message bus in the middle is the thing, of course, that glued everything together. But this was one of the goals that pervaded this architecture, is this idea of shared resources. So one of the things you were instructed to look for within this architecture is exactly this pattern. So let's say you're an insurance company and you have all these different insurance divisions, auto and homeowners, commercial and casualty and life, etc. And one day you notice, hey, look, they all have some concept of customer inside them. So what I'll do is consolidate that into a single customer service and just have all those services reference that guy. And this is certainly one way to do architecture. And there's a definite appeal to this because, hey, now we're reusing everything we know about customer. It turns out, though, there are two big time negative side effects of building an architecture like this. Number one is you've now created a coupling nightmare, because now every time you make a change to customer service, that change ripples out to the rest of your architecture. And if you've built an entire architecture around this idea of extreme reuse, then suddenly what you've built is a really, really brittle system, because everything you change now may cause something else to break because everything has been reused. That's bad enough. But the other thing we realized after building a few systems like this for a while was, if I have to build one customer service that knows everything my entire enterprise knows about customers, it's going to be really complicated because it has to know everything my enterprise knows about customers. And if I'm the travel insurance, I don't really care about all the medical stuff and the commercial insurance. I just need some customer stuff that I can do. But by trying to drive this level of reuse, it makes everything in your architecture as complex as it can possibly be. And that's probably not what your goal was. I've said a lot of bad things about this architecture. The good part of this architecture is here. And this is your new favorite party phrase, protocol agnostic heterogeneous interoperability. Okay, what does that mean? Well, let's go from the right to the left. Interoperability means things calling each other, and heterogeneous interoperability means different kinds of things calling one another. So in this architecture, in this kind of orchestration-driven SOA, you could have Java call .NET stuff, which you could call PHP stuff, and it didn't really matter. So that's protocol, that's heterogeneous interoperability. In fact, because that message bus also acted as an integration hub, you didn't even have to know what protocol you were calling, as long as the enterprise bus knew about it. So if I viewed the world as SOAP, but the rest of the world viewed it as a gRPC, then that message bus will just take care of that transformation for me invisibly. So that's protocol agnostic heterogeneous interoperability. It turns out that microservices is one less than this. It's typically protocol aware heterogeneous interoperability, because you typically don't have big coupling parts in your architecture like integration hubs in microservices. Contract decoupling was another great feature here, and you could build all these contract rules in the middle of the architecture as a way of doing reuse. The other good thing about this, and the place you still see this style of architecture, is in integration-heavy environments, because any of those enterprise services could actually be packaged software instead of custom software, and so you can allow things to mix and match in this architecture and gradually replace things over time. So the real driver for this architecture in this day and age would be integration, and orchestration. Yes, I realize I put integration on there twice. But the other thing to think about this architecture and this discussion we had earlier of domain versus technical partitioning, where does catalog checkout live in this architecture? And the answer is everywhere. It's like you've ground up your domain into a fine powder and sprinkled it over the top of this architecture. It is so hard to make changes to anything in your domain in this architecture because it's all split out as far as possible. This is as far as I think we will ever go toward just pure technical partitioning, because it just obliterates the domain. So the last of these that I'll talk about are serverless architectures. And we didn't actually include this architectural style in our book for a reason I'll get into in just a second. But these go broadly into two families, backend as a service and functions as a service. And there's a third category that some people try to lump in here, which is I'm running Kubernetes on the cloud, but that's not really serverless. You have a server, it's your container, you're just managing it on the cloud. So these are the two true serverless style architectures. The first of these backends is, of course, the defining characteristic here is that it's somebody else's computer. I don't have to manage all the resources. The original, when it first came out, this had a lot of interest, this idea of backend as a service, where if you look at a traditional application with something like a browser and a server and a database, backend as a service said, well, let's find backend databases that will handle this, like, you know, something on GCP or Amazon, where I can just put all that data there, and I can build an API gateway to kind of coordinate between those two. And I can find somebody else to do an authentication service for me. So it's finding all these services that are already out there, just wiring them together, integration architecture style. One side effect of this is that code that used to reside primarily on the server side now has to move up to the browser because that's where you have places you can put code. Like I say, this started out as the leading thing in serverless because it was very easy to do, and then kind of faded away as Lambda got really popular, but this is coming back really strongly. There's a platform called Jamstack that does Java, and it's basically serverless applications using basically this backend as a service pattern. And so Jamstack is actually getting quite a bit of traction these days. The other one that we know, of course, and the one that's most heavily used, is this idea of lambdas and functions as a service. All the major cloud providers now have some of this capability. And they're basically building more and more back-end capabilities, API gateways and databases and search facilities and AI, machine learning, and all those sorts of things. And so the real driver, the obvious driver here is a high degree of agility. You don't have to mess with anybody in an organization to get resources. It's all just availably there, but works very well for very discrete things right now. But there is a perspective that I think it's worth adopting for serverless for right now. So one of the interesting things about architecture, of course, is that it's constantly moving and shifting and changing. I went back to this, I'll go back to something I said as I started talking. One of the things that Mark and I wanted to do when we wrote the Fundamentals of Software Architecture book was realize that the world keeps changing in the software development ecosystem. If you look at a book about software architecture written 20 years ago, they were literally describing a different place. And we fully expect that somebody else will write another Fundamentals of Software Architecture book in another 10 years, and it will be describing a different place. And so I believe that serverless will continue growing and become more and more viable. But for right now, I still believe it suffers from this thing we identified in the Evolutionary Architectures book called the last 10% trap. And this is based on some experience I had many, many years ago. I used to work in a consulting company, and one of the things that we did was build Microsoft Access projects for clients. And we ended up shutting down that part of the business because we noticed a common characteristic. Every single one of these projects started as a booming success and then ended in total failure. And we wanted to understand why that kept happening over and over again. And we codified that as the last 10% trap. So if you look at a tool like Access, and if you look at the totality of what the user wants, the first 80% of what they want, it's amazing how fast you can get there. And in fact, everybody's always super happy about how much progress you can make right away. The next 10% is possible, but difficult, because now you're trying to do something the tool wasn't really designed to do, but you can kind of hack it and bend it and cheat a little and figure out how to get it to do it. Problem though, is that last 10% is impossible. And users always want 100% of what they want, and they're never satisfied with less. And so that causes us to always abandon these projects. Right now, serverless looks to me exactly like this, because it prototypes great. It's easy to put stuff up there, but then you see all these hacks about things pinging other things to keep them alive and hot, etc. This also answers the questions that some of you may have pondered at some point about whatever happened to all the 4GLs. Paradox, DBase, Visual Foxpro, they all suffered from the last 10% trap, and we always go back to general purpose languages and general purpose architecture styles to solve these problems. Serverless may eventually grow up to be a full-blown architecture style. I just don't think it's there yet, because to me it looks like it has all the hallmarks of the last 10% trap. So let's move on to the next category, which are the domain-centric architectures. There are three here. One I've already talked about, the idea of the modular monolith. And I won't say a lot more about this. The idea here is building things partitioned around domains or workflows rather than technical capabilities. The obvious drivers here is you're more closely adhering to Conway's law, and you're separating things that in your architecture the way they're separated in the real world. This, of course, heavily relies on the ideas in domain-driven design. So if you're doing domain-driven design or event storming, this architecture works very, very well. The other architecture heavily based on domain-driven design is everyone's favorite cool kid architecture, which is microservices. This is a distributed architecture where each of these components are meant to be distributed independently of one another and talk over network protocols. This is protocol-aware heterogeneous interoperability. As I mentioned before, one of the main drivers in this architecture is extreme levels of decoupling. Therefore, you tend not to see things like integration hubs here that couple everything together. That's really the driving philosophy of this architecture, is high levels of decoupling. And it drives a lot of the decisions in this architecture that might look different otherwise. All of these things are meant to be independently deployed and extremely decoupled from one another. The service component here obviously is very small. That's where the micro comes in, but it shouldn't necessarily be arbitrarily small. So there are a lot of drivers as a developer that drive you toward making it smaller, but then there are things that make you toward bigger. And so some of those things are things like, what is the purpose of this thing? Things like transactions and choreography. So purpose might drive you down to a smaller size, but then if you have to do transactional behavior, you want to try to avoid transactions across microservices as much as possible. Also, if you build a whole bunch of components and then you end up, you're having to do a ton of choreography or orchestration between them, then maybe it's better to bundle them back together. One of the things that developers get in trouble with here is, and this is actually mentioned in the article written by Martin Fowler and James Lewis that popularized microservices, that microservice is a label, it's not a description. This is not a commandment to go make things arbitrarily small. What you're trying to capture here is a bounded context in domain-driven design terms. In fact, if you look at that article that introduced microservices to most of the world, some of their services are pretty big because they're trying to capture a bounded context. So don't get caught up on the micro name in this architecture. Because very often some things will have you, like purpose will drive you smaller toward smaller component sizes, but then other things like transactions will drive you up toward bigger ones because you're trying to avoid things like transactions. The philosophical driver behind this, of course, is this idea of a bounded context. And this is one of the few architectures that includes data as well as any sort of architectural coupling. This is why I say that this drives so many of the decisions in this architecture, because let's say that you have a an address component that a whole bunch of your services need within your ecosystem. Well, normally you just share that across all the services that you want to have common address information. But that creates a coupling point in this architecture. And so the right answer in this architecture might be duplication rather than coupling. If your main goal is to cut down on coupling, then sharing stuff is coupling. So that's how this can drive some fundamental decisions, because what you're doing is looking at a different kind of trade-off. Because if I have a really extremely decoupled system, I can move really fast on an individual service level without worrying about breaking stuff. Now, one of the common compromises you see on that is replicating things at the data level, either through caching or something like that, rather than doing orchestration as a way of spreading information around. You often see microservices written with this API layer, but it's never a mediator in event-driven architecture terms because you don't want to break open that shared context. So it can be used to hide the endpoints of services so that you're not just making requests directly from the outside world. This can also be a proxy for service discovery or user interface, etc. This typically is an event-driven architecture, and as I mentioned before, one of the common optimizations in this architecture to get higher performance is to add events, which gives you scalability of the decoupled services, and events give you a higher degree of performance. There are lots of interesting techniques here, and in fact, I'll touch briefly on some of the analytics stuff at the very end when I talk about patterns, but a lot of press about microservices these days. So extreme degree of modularity, very agile, highly fault tolerant, but extreme scalability, that's the real champion here, and really good support for these agile principles like testability, deployability, etc. So the last of these styles that I'll talk about is a hybrid called a service-based architecture. This is one that's still a distributed architecture and still uses a lot of the same building blocks as microservices, just nowhere near as strict about data independence. There are three main differences between a service-based architecture and microservices, and here are the three. I'll mostly talk about the first two: service granularity and database scope. The other commonality is that you tend to use the same level of automation for tools like continuous integration deployment pipelines in this architecture. So in microservices, obviously the service granularity is very small. In a service-based architecture, you're not trying to get as small as you get in microservices. So service-based architectures are very often the target of a migration from a monolithic architecture into a distributed architecture. So the trade-offs here, probably better performance in a service-based architecture because you're not doing so much at the network level, but more complex to develop services, probably more robustness, but harder to test. You're getting to a domain scope versus a technical partitioning, but things like deployment pipelines get more complex. The biggest headache in microservices, particularly if you're going from another architecture, is the data independence. Well, that doesn't exist in a service-based architecture. This is the pragmatic realization, look, we've been coupled at the database level forever. We know how to handle that, and so we're just going to keep living with that. Maybe some degree of decoupling, but nowhere near the degree of microservices. This may give you much higher performance in a service-based architecture just because you're not splitting all your data apart. The downside, of course, now is you have a coupling point that's sensitive around things like schema changes. Let's move over to the domain-specific architectures, and I'll talk briefly about these guys in the interest of time. Space-based architecture is one that solves a very particular problem. So let's say that you have this setup, and your web server gets hammered. What do? Well, you put more web servers in place, and then your app server gets hammered. So what do? You put more app servers in place. Well, now your database gets hammered. What do? You put more databases in place. Now your database gets hammered. So what do? You put more, I've run out of place to add stuff. This is a problem that companies like Amazon had before the cloud came along, and the solution to this problem was a space-based architecture. It's like I got turned sideways somehow. A space-based architecture is one that has a very specific kind of virtualized middleware that, with all these specialized components to handle this idea of extreme elasticity. So the processing unit here, and there are hundreds of thousands of these running. The space, by the way, refers to tuple space. There are hundreds of thousands of these running within this architecture, and it has whatever behavior you want, but it also has an in-memory data grid that gets replicated through this replication manager. The messaging grid manages requests to each of those services. The data grid manages the replication to and from. So the real trick to this, of course, you can't write 10,000 things to a database all at one time. And so what you can do is spread it across this architecture like a big cache, and then eventually get it down to the database, which is exactly what this is doing. The processing grid handles all the processing chores, and then the database data writer moves all that stuff into and out of the database. So this is a highly, and you can do this on clouds as well. The synchronization between these things can be either asynchronous or synchronous, and there are a bunch of some interesting math that goes along with that I won't talk about here. This is complex enough where products implement this. So here are some of the products that implement this. This is an extreme case for variable scalability. You probably use something like microservices for this now, but this is still shows up in tools like Hazelcast and Coherence, and it's a really good example of what if you design an architecture just around one thing. An even better example of that I'll spend even less time on is LMAX, because there's a great write-up here on the martinfowler.com website. The interesting thing about LMAX is they wanted to see how many transactions per second they could achieve with a single Java thread, and they managed to get 6 million transactions a second. Now, I'm not going to go into this in great detail. Like I said, there's a write-up on Martin's site. I do want to show you, though, the structure that allowed them to do that. This is this architectural component called an input disruptor. This was created by the LMAX team, and what this allows them to do is push things into this ring-shaped queue at an enormous rate. So that business logic processor is the thing that's actually doing work. And so what this architecture does is build this 20-min slot ring queue, put things in there, and then have these processors chase each other around the ring. It replicates these things into more than one slot and basically chases them around this ring by pre-allocating everything, keeping it small enough to stay in memory the entire time. They can actually build an architecture that can support 6 million transactions a second. The output disruptor is much simpler because all it has to do is unmarshal stuff and put it back into the architecture. So an amazing bit of work. And there's a great write-up on Martin's site, as I mentioned, if you're curious about that. Okay, so I'm just about out of time here. And so let me, sorry, I'm trying to find a graceful way to move past some of these slides because I have way too many slides here. And that's what I need to see here. I thought that's what I wanted to see. Okay, sorry. That's what I wanted to see. So I'm just about out of time here. So let me just wrap this up by domain architecture isomorphism. So this is the really important thing. This is what I was talking about before about understanding the underlying philosophy of the architecture. This is a really fancy way of saying make sure that your domain and your architecture match one another. An isomorphism is a mapping from one thing to another, and so make sure that your problem domain is the same shape as your architecture. So for example, microservices is not the solution to every problem. If you have a highly complex problem that has a lot of moving parts, building that as a monolith, at least that part of it, may be a much better solution. So make sure you understand what shape your architecture's in so you can adjust your architecture and choose the best one that causes you the least amount of work. Understand the philosophy behind that style because that allows you to know when you can cheat on it. And for all of that, we talk about these architectures like microkernel and microservices, you almost never see these out in the wild in their unchanged form. They're almost always hybrids and variants. In fact, architecture styles nest inside one another, so I could implement one of my microservices as a microkernel, for example, and so you see these hybrids all over the place. It's also important to distinguish patterns from tools. That mediator pattern shows up in a lot of different tools, and so understanding the fundamentals of the pattern allows you to understand how to use those tools and get out of the hype cycle. And so this is what every beautiful, simple tool grows into, is something that still has the original purpose, but is lost somewhere and all that other stuff. All right, so that's my time. Thank you very much for attending. I hope you enjoyed it, and I hope you learned some stuff about architecture.
Thank you, Neal. That yeah, well, for sure I did, and I'm sure all of our attendees did.
Well, that's the first, Vlad.
Sorry?
That's a first.
Well, I live to surprise people. We also have a couple of questions from the audience.
Okay.
One of them is, how can one avoid the trap of trying the entire evolving plethora of architectural styles? Is it all about learning and experience after all, or what? Or there are some, well, let's say, main principles that could help even beginners discern what's right and what's wrong?
Well, so it's mostly about experience. I mean, one of the things I said was, you know, the main way to tell an architect is someone who's seen enough terrible code bases to know one when they see one the next time. But a lot of it's experience, but a lot of it's just knowledge acquisition. You know, we go through these styles in great detail in our book. If you've gone through all those styles in great detail, when a problem presents itself, the real trick in architecture, and this is very much like design patterns. So all of you who worked your way as a developer know that you can read the design patterns book, but then until you see it in the wild and say, oh yeah, that's one of those things. That's what it really takes is, you know, both reading about it and getting the intellectual thing, but then also recognizing that pattern in the wild. So I think that's why learning and experience go hand in hand in architecture. One of the things that, so the website, fundamentals-of-software-architecture.com, one of the things we have on our website are all these things called architecture katas. And they're a way for brand new architects to practice designing new architectures. Because you've got to practice. How do you get better at anything in life? You practice. How often do you get to practice designing new architectures? Almost never. So how are you supposed to get better at it if you never get a chance to practice it? And so the katas on our website are designed to be these small team-based exercises that give you a chance to practice to get better at it.
Those are useful for certain. Mm-hmm. I mean, yeah, experience does help. with
Absolutely.
everything. Another related question is, if are there such things are fail fast when speaking of impactful architectural decisions, or yeah, do we need to wait until the next project comes along
No,
to?
the critical thing about architecture is iteration. Iterate on your design. You've got to figure out a way to iterate on your design and architecture, because one of the fundamental things that we've learned about software over time is you need a fast feedback loop. The faster the feedback loop you can create on an architecture design, the better off you are. And so you can't test out the entire architecture, but you can certainly test out localized decisions like, I need to make a synchronous call between these two things. So let's see what kind of impact that's going to have on performance and scale, et cetera. And I may need to iterate on that design. So don't think that you're ever going to, in your brain, complete an architecture that just gets built with no changes whatsoever, because the world doesn't work like that. You've got to build the ability to iterate into your design, because the world is going to annoyingly prove you wrong over and over again.
Unfortunately.
Yeah, and then it's also stated in the question, yeah, what's that magic most responsible moment? And yeah, I think this is where the struggle is, right?
Well, I can tell you exactly what the exact responsible moment is. It depends. Because it's not universal for different projects. It's not universal within the same company. So, you know, it's impossible to create a silver bullet that says, this is exactly when you need to make that decision. There's just no way. I mean, if it was, then, you know, software architecture would not be a coveted job. It would be a very, you know, it'd be like working at McDonald's or something. You know, you'd have the button on the cash register that says, make the decision here. It's like, all right, then, you know, what do you do next?
And speaking of this, maybe more a philosophical thing. So there's one last minute question. So people tend indeed to develop affinities towards certain patterns, or like, yeah, this attendee is saying, see everything as a nail for their new hammer. So what's the cure for that?
Well, continued learning and trying to be objective. So Mark Richards, my co-author, has a great phrase. He said, architecture is all the stuff you can't Google. Because when you're a developer, one of the things you get really good at is Googling for solutions for things. Like, oh, there's a blog, and oh, there's a nice Medium post that explains how to do that. Well, as an architect, there's a pretty good chance that the scenario you're looking at has never existed on Earth before. And even if it has, what are the chances that overworked architect took time to write a blog entry about it, explaining to you how to fix that problem? So your job as an architect is not finding silver bullets laying around, because the news is there are very, very few of them. Your job as an architect is, given some brand new situation, and most of them are brand new, how can you objectively assess the trade-offs on either side of this decision and make the most informed decision going forward? That's the job. And if you get really good at objectively doing trade-offs between things, not getting religious about something, but objectively trading them off. So one of the fun things to do is have a discussion where somebody in your organization who's the biggest diehard microservices fan, make them argue for when we should use monoliths. Think about the other side of it. What are the trade-offs? So one of our laws of software architectures is everything in software architecture is a trade-off. And the first corollary is, if you think you found something that isn't a trade-off, you just haven't discovered what the trade-off is yet. And so I think that's really the skill in architecture, is learning to assess new problems and come up with objective sets of trade-offs on either side, because then you don't have to have a crystal ball and you don't have to have a gun loaded with silver bullets. You can make good objective decisions based on engineering going forward.
All right, well, thank you, Neal. I wish we had more time.
Maybe we can do it next time in person.
Hopefully. Somehow I feel that maybe the next time will be online as well, but yeah, let's hope for the best.
See.
All right, thanks a lot.
Thanks very much.
Thank you.
Yeah, and okay, let's regroup in around 6 minutes.